In this lesson, we will learn how to solve rational inequalities. That's an inequality with these fractions that have variables in the numerator, denominator, polynomials as fractions, and everything else. If you don't already know how to do this, I suggest you put your pencil down and just watch me this time, and then pick your pencil back up, pause the video, and try to do this problem by yourself afterwards. That is the best way to learn. Okay, so what you want to do is get 0 on one side. That's going to be our first step. So I'm going to subtract 1/2 from both sides like this. So that's just going to give me 1 over 4a plus 5 over 8a minus 1/2 is less than 0. Okay, so we got 0 on one side. Now I want to combine all of these, so I'm going to need like denominators. Okay. One other thing though before we get started, when you have a subtraction like this, I highly recommend that you change this to addition by adding the opposite and just put that negative sign up in the numerator. Just trust me that this helps avoid certain common mistakes that I see all the time. If there's anything that has to be distributed or anything, this helps make sure that the negative gets distributed. Anyway, we need a common denominator. Now, hopefully you can see that all three of these can be turned into 8a. You know what I mean? 4a, all I got to do is multiply by 2. Alright, over here, if I multiply this by 2a, then that'll make 8a. So we need all three to be the same. So we are going to go ahead and shoot for everything to be 8a. So on this one, we're going to multiply by 2, like I said. That'll make this 8a. So notice I'm not multiplying through the inequality like I would if this were an equal sign. You know, we are doing this differently. It's not your imagination. If this was equals 0, I'd be multiplying through by 8a and canceling everything out. But because it's an inequality, we're not going to handle it that way. Alright, because it's less than, we are going to add all these up, and then I'll tell you what to do. So, okay, so I multiply by 2. This one obviously is already 8a, so I'm not going to change anything. This one, if I multiply by 2, no. That would, if I started to say 2a, but what would that make? 4a. Alright, I want 8a. So I need to multiply by 4a. Okay, like I had over here. So I'm going to multiply this one by 4a. And I'll have to do the same thing in the top, 4a. Okay, so what I have now is I have 2 over 8a plus 5 over 8a plus negative 4a. Alright, I'm going ahead and multiplying those together. So negative 4a over 8a is less than 0. Now that everything has a like denominator, I can add all of these fractions into 1. So if I do that, it's going to look like this. I will keep my common denominator of 8a, and I will add 2 plus 5, and I'm doing plus negative 4a, but now I can go ahead and just put minus 4a. Okay, I'm putting all these together. So obviously I have some like terms right here. 2 plus 5 is 7, so this gives us negative 4a plus 7, okay, over 8a is less than 0. Okay, once you have it simplified down as far as it'll go, alright, just a single simplified fraction, it's time to figure out what the critical values are. So here we're going to do the critical values. Okay, I left out a u. Okay, so the critical values, these are the they are the zeros, of the function, and they are the excluded values. So let's start with the zeros. You will get the zeros of the rational function by setting the numerator equal to 0. Okay? Because that's the only way that this function is going to equal 0 is if the numerator is 0. So let's see. So if we do negative 4a plus 7 is equal to 0, because we're finding the zeros, and subtract 7 from both sides, so that would give us negative 4a is equal to negative 7, and then divide by negative 4 on both sides. Alright, so that's going to give us a is equal to positive 7 over 4. So that's one of our critical values. That's a 0 of the function. Okay? In other words, that's an x-intercept of this function. Now, we also need the excluded values. Let's see, excluded values. Well, we'll just look back. We could look back at the original problem in this case, and the only excluded value is going to be a cannot be 0. These are all monomials here. It's not like a plus 5 or anything like that. So it's just these monomials. So just a factor of a is the only variable factor. So a cannot be 0. Okay, so together these are the critical values, the 0 and the excluded value. So we will use these to start breaking up our number line. Okay, 7/4. That is approximately equal to, let's see, carry the 1. Okay, that's approximately equal to 1.75. So good to keep in mind. Well, actually, it's not approximately. It's exactly 1.75. Just FYI. So let's build our number line now. I'll come back up here again. Alright, so here we go. So the number line is going to be like this. Should I change colors for this number line? I think I will. Alright, so here comes my number line. Got lots of space, so I'm going to use it. I've got to work in my excluded value, so I've got basically 0 and 1.75. Okay, so over here somewhere I'm going to put 0, and then over here I'm going to put that 1.75. I've got lots of space, so I'm spreading out. Okay, now as I form my number line graph, I'm going to ask myself, open circles or closed circles? Because we want the values that are less than 0 but not equal to 0, then my 0 critical value, okay, at 1.75 the function equals 0. Okay, but we don't want to include that in the solution set, so we're going to leave that as an open circle, because we don't want what equals 0, we only want what is less than 0. So we're going to leave out values that give us equal to 0, like 1.75. Anyway, of course, the excluded value of 0, excluded values will always be open circles. Okay, I feel like I should write that down or something. Alright, excluded values are always open circles. Okay, because the values are what? Excluded. So they are to never be included in the solution set. So if you want to exclude something, you make it an open circle. So this should be looking familiar. And why is that circle so big and this one so small? I don't know. Why are you so critical? That's what I want to know. Why are you judging me? Don't judge. This is hard enough as it is. So this is probably looking familiar to you at this point. I'm going to make that chart that we make sometimes. And because we're doing test values, that's right. It's back again. All right. This is what we do anytime we're doing an inequality with really any kind of a function. So we need a test value in each one of the zones that are created by these critical values. So over here on the left, I need something less than 0. How about evaluate the function at -1? Why not? Now here I need something between 0 and 1.75. How about 1? Seems like a nice value to use. Now how about something bigger than 1.75? How about 2? So there are other values you could use, but these will work just fine. Okay, so let's evaluate the function and find out if the function is less than 0 at these test values. So I think the easiest thing to do is go back to one of our early well, you know what, let's just keep it. Let's use this. Let's use this form. And I'm going to use my calculator, my TI-30XS Multiview. So handy, so helpful. I'm going to use the table feature, so I hit that table button to the rescue, and I'm going to type in this function. So -4, I'm going to use x's, so -4x plus 7, fraction mode, -4x plus 7 over, what was it, 8x? Okay. So I hit enter. Now ask me where I want to start. Well, I am testing these critical values here, so I'm going to start at -1. So yeah, how about that? Let's start at -1. Okay, so at -1, the function has a value of -11/8. So the question is -11/8, and remember we want our values to be less than 0. So is -11/8 less than 0? Alright, and of course the answer there is a big yes. Okay, all negative numbers are less than 0. Now let's look at a value of the function at 1. Well, at 1, the function has a value of 3/8. So is 3/8 less than 0? I should put a question mark on here. And the answer to this question is no. That's a positive number. Positive numbers are greater than 0. And now we have to check one more value, the value of the function at 2. So I'm going to scroll down a bit. At 2, the value of the function is -1/16. Okay, so is -1/16 less than 0? And of course the answer is yes. That's a negative number, so of course it's less than 0. So the yeses mean that these test values are solutions. The no means that this value is not a solution. Alright, if one test value is a solution, then all of the values in that zone are solutions. So because -1 is a solution, then all of these values are solutions, and we'll show it by making this arrow. Alright, because 1 is not a solution, that means none of these points in here are, so we will leave it empty. Because 2 is a solution, then everything in this zone is a solution. Okay, so there is your number line graph. Isn't it beautiful? Now we will go ahead and write the interval notation. Okay, they're talking about like the way we do domain or range. So looking at this arrow over here, this is these values go from negative infinity, all right, coming from the far left, to 0. All right, and we'll leave it round parenthesis because we're not including the 0. And then we'll say union because we're joining it together with this other part of the interval. And it picks up here at 1.75. Or indeed, I could have used, I could have said 7 over 4, which is probably, that's what I'm going to do instead. All right, it was fine to use 1.75 because that was an exact value. But sometimes you have some decimal that's like rounded, so it's safer. It's safer to use the fraction. So 7/4, and it goes from there up. So to infinity. Okay, so this is the complete answer to the problem. All right, our number line, graph, and interval notation. So that's what you want to have for all problems. Okay, brilliant. All right, this video may be a little long because I'm already at 16 minutes and I feel like I just got started. Nevertheless, I'm going to go ahead and do number 2 on the same video. And so, like I said, I'm going to move this over to the other side. Now, I am subtracting 29 over x from both sides. That's what I'm doing. So these will cancel out, and I'll have a negative 29 over x. Now, I don't feel like taking up all that space. So I hope you'll let me just show it by doing 2 over x plus 3 minus 29 over x is greater than 0. But understand that I just subtracted 29 over x from both sides. Okay, if it helps, if it makes you feel better, look at this as like 3 over 1, if it makes you feel better. Now, we need all the denominators to be the same. Okay, so I've already got 2 x's going on, so this is going to need to be an x as well. Okay, and I can make it an x as long as I do x in the numerator and the denominator. Now they're all the same. Okay, so what I'm going to have when I combine these into 1 is I have 2 plus 3x minus 29 over x is greater than 0. No, I cannot cancel out these x's. Alright, they're connected by addition and subtraction. But what I can do is combine these like terms. So I'll have 3x minus 27 over x is greater than 0. So this is a simplified expression. Okay, just double checking. So that's as far as we can go here. So now let's get our critical values. Critical values. Alright, that's zeros and excluded values. So let's start with zeros. Okay, for the zeros, I will set this, equal to 0. So adding 27 to both sides, I get 3x is equal to 27. And I divide by 3, and I get x is equal to 9. Okay, so that is one of my zeros. Well, that is the only 0, so that's a critical value. Now let's talk excluded values. Let's see, let's look back. Alright, right here I can see that x cannot be 0 and nothing canceled out or anything, so x can't be 0. That's the only excluded value. X cannot equal 0. So these are my critical values, 9 and 0. So let's go build a number line for this thing. Okay, 9 and 0. So here's 0, here's 9. Okay. So at 9, open circle or closed circle. Understanding that the value of this expression is 0 at 9. Well, I only want values that are greater than 0, not equal to 0 like this gives. So I don't want to include the value at 9. 9 is not a solution. So I will have to leave this as an open circle. Of course, excluded values are always open circles. Always open circles. Alright, they're excluded. Open circles are how we show that something is excluded. So at 0, I'm going to rock the open circle once again. So I am going to use the divisions in the number line that we just created. Alright, I'm going to use that to choose my test values. So over here to the left of 0, let's take a look at the value of the function at -1. Here between 0 and 9, why not just use the value of the function at 1? But you could use 2, 3, 4, 5, 6, 7, 8, even a decimal if you want to. It really doesn't matter. And here I'm going to use f at 10. I just needed something bigger than 9. So I'm going to test each one of these values. Now to do my test, I'm going to use this right here. Okay, this version of the function. So 3x minus 27 over x. And I'm going to use my TI-30 XS multi-view. Hit the table button. Alright, 3x minus 27 over x. Alright, we had critical values. Well, our first test value is -1. So let's tell it to start at -1, because why not? Okay, at -1 we have a value of 30. So the question is 30 greater than 0? Alright, and obviously the answer is yes, of course, 30 is greater than 0. Alright, what about the value of the function at 1? Well, at 1 the function has a value of -24. So the question is -24 greater than 0? And obviously the answer here is no. Negative numbers are less than 0. And last we need to check out the value of the function at 10. So I'm going to scroll down a bit. Okay, at 10 the value of the function is 3/10. Okay, so is 3/10 greater than 0? And the answer is yes, it is. It's a positive number, so of course it's greater than 0. So the yeses mean that these test values are solutions to the inequality. And if -1 is a solution, then all of the values in this zone are solutions. I will show that with an arrow. 1 was not a solution. That means none of these values are solutions. 10 is a solution, yes. So that means all of these values in this interval are solutions. Okay, so that's the graph. Let's cap it off with some interval notation. So this piece over here comes in from -infinity and goes to 0. Not including the 0, so leave it around parenthesis. Then we pick up with 9, which we will leave round for the same reason. So above 9, so that's 9 to positive infinity. So this is interval notation. Alright, so together this is the answer. Alright, we've got the number line graph and the interval notation. That's what we were supposed to find. Okay, soak in the beauty of it. It's awesome. So that was the answer to number 2. And I'm going to go ahead and stop this video here because it's plenty long. And but if you need to see more further examples, I have 2 more problems coming on the next video.